Hi, everyone. Thank you and welcome to the talk. My name is Xiaoning. In this talk, my colleague Qian and I will talk about the multi-tenancy work we did in Kubernetes. Qian, do you want to quickly introduce yourself?
And I'm a cloud dev engineer in Futurewei, and my focus now is in multi-tenancy work in Kubernetes. Thank you.
Okay. This is the agenda of the talk. First, I will give a brief overview of the project, including some necessary background information. And then, for the most of the part, we will walk through our multi-tenancy design and features. After that, I will also give a summary about the current project status, the next step, and the challenges. And we will conclude the talk with a demo. Okay, let's get started with the overview. First, I want to say multi-tenancy is actually a very broad topic in Kubernetes. There are different multi-tenancy models for different scenarios. And we usually categorize these different models by their isolation level. If a multi-tenancy model provides strong isolation, we say it's a hard model. If the model provides a weak isolation, we say it's a soft model. For some use cases, weak isolation probably is enough. For example, if you are working with multiple teams inside a company, because these teams all belong to the same company, there is a certain level of trust among these teams. So you don't need a very strict isolation. It's probably okay for them to see some resources from each other, and they probably can even coordinate on some resource allocations, like the IP range. But if you are working with multiple external organizations, there's no trust among them, and you need a hard isolation. That's our use case. In our use case, we want to enable multiple external organizations to share a same physical cluster. And we don't assume any trust relationship among these tenants. A typical example is a cloud provider offers a Kubernetes cluster as a service to public cloud users. And obviously, there's no trust among these public cloud users. So we are trying to address a hard multi-tenancy model with strong isolation. While we'll talk about the detailed design and features in the next slides, here I want to quickly describe our solution from the following three aspects. First, our whole solution is built around the idea of virtual cluster. So there is only one physical cluster and one control plane. But each tenant feels like they are using the cluster in an exclusive way. They are not impacted by other tenants, and yet they even do not realize the existence of other tenants. We also provide API backward compatibility. So all the tenants can still use their old Kubernetes tools and clients. All the APIs are same. They don't need to change any code or YAML files. Everything is transparent. API is all same. And we also provide some self-management. Tenant admins can manage their own tenant without getting help from class admin. They can still use like the native Kubernetes objects, like rule settings, rule bindings, cluster rule, quota, security policies. They can still use all these familiar API objects, and all these changes only apply to its own tenant. It won't impact other tenants. All our work is implemented in an open source project called Arctos. I put the repo URL here. Feel free to check out if you are interested in the project details. After the overview, let's walk through our design and features. First, I want to start with a very fundamental concept called space. Space is a new concept that we introduced in API Server. a space is a higher level of isolation unit beyond the namespace. A space can contain any API object. You can think of a space as a subfolder. When you create a subfolder, you can put anything in the root folder into the subfolder. So here I put an example. We have two objects under the space called T1. If you look at the left side of the example, so this T1 space has a pod resource, which is a namespace scoped, and it has a PV object, which is non-namespace scoped. In the URL, due to some historical reasons, we are still using tenants, but it should be spaces. And on the right side, you can see how these objects are persisted in etcd. We basically embedded the space name in the etcd key, so all these objects are stored separately. You don't need to worry about naming conflicts. After we introduce the space, every API object in API server belongs to one space and only one space. In order for us to quickly find out which space contains this API object, we introduce a new field in the object metadata section. So every time when you check this field, you can easily find out which space this object belongs to. Okay, so we introduce a space, and each tenant can have its own space, and in the space he can have its own copy of the resource hierarchy, and he doesn't need to worry about naming conflicts and any other conflicts with other tenants. But how does space get related with tenants, and how did it get initialized? Basically, there is one special space called a system space. This space is created automatically during cluster bootstrap. So after a cluster is bootstrapped, there's only one space, system space there. And this system space contains all the cluster level resources like cluster settings and nodes, etc. Because this resource, they don't belong to any particular tenants. And in the system space, we introduced a new API object called tenant. I put a sample YAML file here on the right side. You can see it's a pretty simple object. It also has a tenant controller. Like any other controller in the Kubernetes, this tenant controller watches the life cycle of these tenant objects. Whenever a new tenant object is created, this tenant controller will kick in. It will create a corresponding space with the same name of the tenant. And it will also initialize this space to create all the default objects, like the default namespaces, default rules, default DNS, all this stuff. So it will initialize this space and make it look like exactly the same as the original, the Kubernetes API server. And also, if a tenant object is deleted, this tenant controller will kick in and destroy the space and delete all the resources in the space. So this is how a tenant space gets created and gets initialized. And next, I will hand over to Qian. She will explain how we build all the other features on top of this fundamental concept space.
Hi, thanks to Xiaoning. This is Qian. So I will give more details about our work. As mentioned by Xiaoning just now, one of the key goals in our design is backwards compatibility. We would like the user. Oh, sorry, I forgot to move the slides. So here the slide I'm talking to. So we would like our customer continue to use current tool like kubectl and continue to use the resource YAML files and the CRD operators without any code change, without code recompiling, or without pod image rebuilding. How to do it? The key design here is something we call short path resolution. It makes the existing APIs will continue to work in our system. Short path is something same as the existing APIs, so it contrasts with something we call full path. The full path, maybe you have seen it just now in the previous slides. It's such a URL with the tenants specified in the path. So with this path, you can uniquely identify a resource in the system, and the short path is without this part. So it's the same as existing APIs, but how to translate short path to full path? So we may have two customers, two tenants, send out two APIs with the same URLs, but we know they need to go to different space. How to do it? We add a component called short path resolution. The short path resolution will infer the target space from the access credentials in this resource request. So after the resolution, this short path will be translated into full path, and then you will go to the correct space. So that is something we do for backwards compatibility. As mentioned by just now, we said that we need the credentials include the user tenant information. So we made some change in authentication. The main change here is we add a new field called tenant in the user identity in addition to current user and group fields. Here I show some examples here. So this one is the new way to generate a cert. And this is a new format for the for the token, and this one is the new format for the password file. So basically we support all authentication strategies that is working in Kubernetes now. And the next thing I would like to say, it's about authorization in our system. It's pretty similar to what we have now. Actually, the main change is here. We add some check on the user tenant. We make sure the user tenant have access to the resource, to the space of the resource. So the rule here is the system tenant can access any space, but if it's just a regular tenant, he can only visit his own space. We may have some cross tenants or cross space visit in the future, but now it's the rule that we have done. And you can see it's actually just add a few lines here, and then after that we make sure the user tenant is in the right space, and then the access control inside the space is same as what we have now in a Kubernetes cluster. So that is access control. And in the next slides, I want to combine what I talk about short path and access and control to give a full story on how a resource request is handled in our system. So suppose there is a resource request arrives, and then the API server will retrieve the tenant and user identity from the request first. And then the next thing it will do is to check whether or not it's a short path by looking to whether or not the space is defined in the URL. If it's not defined, then it's something we call short path. Okay, then we will set the resource space to the tenant name. That's something earlier we mentioned, it's short path resolution. If it's a full path, and we'll do some access control, we'll do some authorization check to make sure whether or not the tenant is visiting his own space. If it's not, and we will check whether or not the cross-tenant policy is allowed, whether the cross-tenant policy allows this request. If yes, then we are here. Then we will access the resource with the full path. Then what is happening next is same as something we will see in the Kubernetes. So that's access control and short path, how they are fit together. Just now, I mentioned about backwards compatibility, that we said every tenant can use their existing code, existing tools without any change, because they are working in their own space. But there are some components that we realize, there are some components they need to work across the spaces. something like a scheduler, like a kubelet, and like all the controllers and the Kubernetes, they are now working with API server, which supports multi-tenancy, and they have to make some code change. So we did it. What we did first is to make some code change to client Go. So we add a set of multi-tenancy CRUD APIs. The difference is now in this APIs, there is a new parameter called tenant. And also we make some code change to support cross-space lease watch. And after that, we made some code change to this components using this client Go new APIs. So here I gave some sample change. Here, like for this one, it's about visiting pods and for a given namespace, and now we need to pass in another parameter, which is tenant. And one thing I would like to mention here is that the code change here is quite straightforward. It's with the new client Go APIs, the change will happen to this scheduler, kubelet, and controllers. It's not big. We have finished it, almost all of it. And scheduler, kubelet is working in our system now, and I think there are 15 or something. I think the number is pretty big, but we did pretty quickly. So if you have interest, take a look at our code, and you can see that code change is quite easy. That's client Go and controller change. And next thing is here, I want to mention that it's something Xiaoning just now gave a very brief description. It's tenant autonomy. As we would like to design the system in such a way, it's like each tenant is working with his own virtual cluster, just like a virtual cluster is delegated to the tenant, and the tenant can manage its own cluster without turning to cluster admins. So he can work with almost all the existing APIs like role bindings, class role bindings, resource code, and things like this. And also here you can see we set CRD. I mean, each tenant can have his own CRDs. And one thing here, like there are some cluster scope concepts like cluster roles, which in existing Kubernetes, it's a cluster scope objects. Now in our system, it's transparently translated to a space level objects. Like here, there's two pictures explain this difference. Like earlier, like the cluster roles, it's effective in all the namespace in one cluster, but now it's working on a virtual cluster level. So this cluster role defined by this tenant will work only in his own space and has no effects on other tenants. So it's something we call tenant autonomy. So each tenant have his own virtual cluster. Next, and something like, I briefly mentioned just now, multi-tenancy CRD. So CRD is a very important feature for Kubernetes, and now we allow each tenant to define his own CRD. They don't need to worry about any conflicts with other tenants, and they can use their own CRD just like they own their own clusters. And this installed CRD is only visible, only usable to himself, to his own space. And the nice thing is because our backwards compatibility, they don't need to change their CRD YAML file. They don't need to change their custom resource YAML file, and they don't need to make any change to their CRD operator. They can just work. And besides this, we also realize there are some requirements that at some point the cluster admin would like to enforce the CRD which is usable by all the regular tenants. We also support this scenario. We call a system CRD. And it's such a CRD that it can only be installed by system tenant in the system space. And we would like to mark it, and we want it to be marked with a special label. Without this label, then such a CRD will be only available to the system space. But once it's marked with special label, then all the tenants can use it, just like his own CRD. So here ends my brief introduction. Next, I would like to hand it back to Xiaoning, and he will give more details. Thank you.
Thank you, Qian. In the previous slides, Qian and I talked about all the design and the changes in the control plane, in the master part, like the API server and the controllers. Here, I want to talk about some changes in the data plane. In other words, things happening on the workloads. The first part is about the runtime isolation. As we all know, regular containers like Docker containers, they are actually sharing the same host OS kernel. But when we are running in a strong isolated multi-tenancy cluster, a single worker machine can run workloads from different tenants. And there might be some malicious users or codes inside the workloads. So it's not acceptable to share a same copy of host kernel. To address this problem, we are currently using Kata to support the OS kernel isolation. And we are also actively investigating lightweight virtualization approach to provide better performance while maintaining the isolation level. The next part is storage. Most of the modern storage providers, they already provide either account-based or volume-based isolation. So there really isn't much work to do here in terms of storage isolation. We only added some tenant-level storage quota to manage the storage quota among different tenants. The most complicated part is actually about network. In the vanilla Kubernetes, the network model is a flat model. It assumes every pod is reachable from another pod, and they all share a single pod IP side range and the service IP side range. But as you can imagine, this cannot work in a hard multi-tenancy model. Because in a hard multi-tenancy model, each tenant is supposed to be strictly isolated from other tenants, and they shouldn't be aware of the existence of other tenants. So then the pod IP side range need to be isolated, and each tenant should have the freedom to choose their own IP range without worrying about the IP conflicts. And the service IP range same needs to be isolated, and also each tenant should have their own DNS, and all this stuff should be isolated. In our solution, we choose VPC network to provide strict isolation. But at the same time, we also want to support other other long VPC network for easy adoption. In order to make the design consistent and support different network providers, we introduce a new network API object. The name is network. And a network object represents an isolated virtual network. And each this network has its own pod IP range, service IP range, DNS service, policies. Everything is isolated with this network object. And a network object can be of any type, either VPC-backed or non-VPC-backed. And for each type, there will be a network provider deployed in system space, just like how CRD and operator works. All the pods, their pods and service and other network-related objects, they are annotated to attach to a specific network. If we look at the example here, in the red space, you can see there are 3 network objects: default, net A, and net B. So any pod or service can be attached to any network. If a pod or service is not annotated, by default, it will be attached to the default network. And this default network object is created by the tenant controller automatically during the space initialization. Here, I want to give a brief summary of the current project status, next, and challenges. Currently in Actos, we already finished pretty much the mostly common used functionalities, like the tenant initialization, tenant deletion, and the commonly used functionality objects like pause, namespaces, replica sets, deployments, job, stateful set, all this commonly used functionality objects, and also commonly used management objects like rule binding, class rule binding, resource quota, etc. Now we are working on the multi-network. In terms of the next step, we are planning on two things. First, we want to support the tenant level resource quota, rate limit, and perf isolation. Since our solution is based on virtual cluster model, different tenants share a same control plane. So this is to prevent a tenant from abuse the control plane, and it won't cause any, to make sure it won't cause any performance impact on other tenants. And the second thing is about the cross-tenant access and fine granular access control for system tenant. Because in the current model, system tenant users can access any other regular tenants. It's like a super user. But the next step, we are going to introduce fine granular access control. So we can reduce the use of this super user. Talking about challenges, we can see there are two challenges. First, our solution has a lot of entry code changes, like the endpoint resolution in the API server and some controller changes, client goal changes. We are thinking about how we can optimize this and reduce entry code changes. And also the second one is about the client goal and controller code changes. We need to add a new parameter called talent for announce our CRUD and list watch methods. But unfortunately, because Golang doesn't support the method overloading, so we have to create a new function for each of these changes. Next, we are thinking about how we can use some other methods approaches like context-based or implicit context to reduce this kind of code changes. That's pretty much Qian I want to talk about today. And here is a list of links about our work. As I mentioned earlier, all our work is done in an open source project called Actos. Here is a link to the project repo, design documents, our roadmap, and the detailed design docs. Everything is public. You are also welcome to join our Slack channel.
Hey, welcome to the demo.
Next,
Here,
I will play a
have
recorded demo
Each
video
of them
made by
corresponds
Qian.
to a session for a different tenant. This one is for the system tenant, and these two are for two regular tenants, which I just created. We explain in the presentation that each tenant is working like owning its own virtual cluster. So when a tenant is created, some resources have already been created for it, just like some resources have already been created when the cluster, the Kubernetes cluster is up. So here we can take a look. Like in this tenant, some namespaces already been created, same here. And some cluster roles have already been created, like here, and also here. And of course, each tenant can create their own resources. Say, this tenant would like to create a new namespace, and you can do it. And then we can see, yeah, it's created. But for this tenant, okay, no new namespaces is created. So everything remains the same. So here we can see the resources management between different tenants are isolated. And next thing I want to show is the creation of the deployment. And here I have the deployment YAML file. Let's take a look at first. And you can see it's just a YAML file, same as any YAML file we can see in Kubernetes, and let's run it. And you can see it's up. So we can have a check here. Okay, we can see the deployments here. But for this tenant, okay, resource creation is isolated. No new deployment here. And also, earlier I mentioned like cluster role, which is working as a cluster scope object in Kubernetes. Now it's working at the tenant space level in our system, and it's done transparently to the customer. Let me show it. So here I'm going to create a cluster role. And that's the YAML file. And here we go. And we're going to create it. Okay, and here you can see. No. Yeah, and you can see the new role is here. But for this one, okay, you see there is no new cluster role. So that's what we say the cluster scope objects is now working at a space level. And we also mentioned each tenant can create their own CRD. And this time we are going to play with this tenant. Okay, so and then we are going to run it. Okay, it's created. Then we can take a look at the CRD here. Okay, and this CRD, just like the CRD in Kubernetes, you can treat it like API resource, and this command will work. But for this one, okay, he knows nothing here. And also we can create custom resource based on the CRD. Okay, then we can check it using this command. And here it is. And for the system tenants, as we mentioned, it has access to the spaces of the regular tenants. So he can take a look at the resources in those regular tenants. Like he can take a look at the namespaces in this tenant. You can see there are 4, 3 which are created by the system automatically, and the one we just created. And also he can take a look at the other tenant. And you'll see here there are only 3. Here ends our demo. Thank you very much. And thank you very much. Okay.
Hi, everyone. This is Xiaoning. Qian and I will take the questions asked during the presentation. And first, I want to apologize. Sorry, due to some technical problems, I think the demo sound wasn't playing out, so it didn't work very well. I guess we have 5 minutes to answer all the questions. Qian and I will address these questions based on the order it showed on the platform. The first question is from Mike Brazer. Does the virtual cluster pass the kube conformance test? Yes, that's our target. And we haven't performed the conformance test yet because we are still working on some the multi-networking part. Um,
Okay.
Chen, are you able to see the question list?
Yes, okay. Like I'll take next question. That's question number 3 from Sugandar Agrawal. So, what's the difference? The question is, what's the difference between space and Kubernetes namespace? Fundamentally, space is a higher level hierarchy above namespace. So, under one namespace, you can have different namespaces, and it's possible that you can have two namespaces with the same name under two different spaces. So it's a higher level than namespace. That's, I think Xiaoning has slides on this, but basically that's just it's a higher level of hierarchy. That's it.
Yeah, yes. As a space is actually a higher level isolation unit than namespace. A space can also contain long namespaced objects like cluster rules or PVs. So it's more like a virtual cluster. It's larger than namespace. The next question is from Marcel von Maltese. What's your security model? Basically, what are the shared resources among tenants? Actually, there are in our model, there are first, each space are strictly isolated. There's no shared resource among spaces. Some physical, some cluster resource like nodes, they are in system space and they can be used by each tenant. But each tenant cannot access this system space directly. They can only be used by the system controllers. What mechanisms are actually doing the isolation between tenants? First, on the storage side, I mean, on the etcd, all the tenant resources are saved on the different key prefix, so they are totally isolated. And the second, when clients try to access this resource in API server, there is the authorization and the authentication mechanism. We make sure a tenant client can only access the resource object that has been authorized to him. And the third, in all the controllers, like deployment controller or replica set controller, they are aware of tenants. When they associate different objects, like associating a replica set to a pod, they only associate the resource among inside a tenant. I think these three sides build the tenant isolation.
Okay. So next one is question number 6 from Bijan Wu. I hope I pronounced this name correctly. The question is this behavior you are describing a custom Kubernetes distribution or extension, for example, the stock Kubernetes? Actually, what we are describing here today, it's more like a custom Kubernetes distribution, involves some in-tree change, as we described just now. Like we have some change to the API server and to the controllers Kubernetes, and also we had to add some new APIs to client Go. But one thing we would like to emphasize is we have some designs for backwards compatibility. So all the existing CRDs, all the existing YAML files, and all the existing tools continue to work. I hope that answers your question.
Yeah, and I probably can add one couple more sentences. Basically, we are describing a standalone project, open source project. It's called Actos. Actos is derived from Kubernetes repo code base, but it's a standalone project and it's using for the cloud infrastructure area. So it's not a add-on Kubernetes add-on. It's not also a Kubernetes distribution. It's a standalone project, open source project. The next question is from Bram Natchgal. Does it also work when using a service mesh? Yes, we are working on the network solution. Once the network solution is done, the service mesh should also work. Okay, I guess we have only 1 minute remaining, so probably we won't be able to take all the questions. Let me see if there are any other important one. I'm sorry if because the platform limited our time, it just popped out a warning window for the 1 minute limit. One question is okay, the one.
Okay, I think for question number 11, yes, it's an open source project. I think that's a quick answer.
Yes, it's this everything is open and public. I put the link there, and somebody asked if we can share the slides, and also because today the recorded demo video didn't play well, I will put the link to the slides and probably also the demo video on our GitHub wiki page homepage, so you can watch it there. Okay, I guess we are probably
we are out.
The time is out, and I think we are cut off from the platform, from the live.